Today we're going to talk about the graphs of polynomial functions, just some basic characteristics of the graph. So to kind of get an idea, let's look at something that we're familiar with. This is a quadratic function here in intercept form. We have an intercept at positive 5, 0 and negative 2, 0. So this is a second degree function. The leading coefficient here is negative 2. Our x-intercepts, the number of x-intercepts, we have 2. And we don't really need to be that specific with this graph. We know that since it is a negative leading coefficient that this parabola or quadratic is going to open down. So it should look something like that. And then the number of turning points, again, I'm not asking you what the turning point is, what that minimum or maximum value is. I'm asking you how many are there. And there is just one of them. We turn right here. Okay, so this was a second degree function. We had 2 x-intercepts. Our leading coefficient was at negative 2, and we had 1 turning point. So keep that in mind as we go through these other examples. Now, example 1, we're adding this, x minus 4 factor to this, and look at how the graph changed. We still had our 2 x-intercepts from above, but our end behavior is different. So this is a third degree function. Our leading coefficient is still negative 2. I don't know when it's at. Okay. So in example 1 is the same equation as above, but we added this x minus 4 factor. So you can see the graph is a little bit different. Now that we have 3 x-intercepts, our end behavior is different. Our degree is now 3, since we have 3 factors. Leading coefficient is still negative 2. Number of zeros, we have 1, 2, 3. And it might be a good idea to start writing these zeros down or putting them in intercept form or points. So we have 3 zeros. We have 5, 0, negative 2, 0, and 4, 0. Just because it's good to have the practice of being able to look at your graph, your graph or your function, and being able to identify the x-intercepts. And the number of turning points, we have 1 turning point here, and we have 1 turning point here. Your turning points are where we change directions, so we have 2 turning points. Here we have another factor added. So look, this 3x right here, that is another factor that would look like this. And we don't need to write the minus 0 part. So that's why it's written the way it is up here in the original function, because we don't need to write x minus 0. But we have now 4 x-intercepts. Right, 1, 2, 3, 4. This is a 4th degree function. My leading coefficient is this negative 3. So now negative 3. My leading coefficient is this positive 3. In distinct real zeros, we have 4 of them. And again, we can just write them down quickly for our information. We have negative 3, 0. We have 0, 0. We have 2, 0, and 4, 0. And the number of turning points. We have 1, 2, 3. So we have 3 turning points. So this problem looks a little bit different. We have an x plus 2 squared right here. So that will change our degree and our zeros when we get to that, and I'll show you how. But our degree is 3. Remember from the other day, 2 plus an invisible 1 that we don't write means we have a degree of 3. The leading coefficient is that number in front, which is an invisible 1 in this case, and the number of distinct real zeros. What distinct means, it means different. Different. How many different zeros do we have here? Well, if we look at the graph, we have 1, 2. We have 2 different zeros, and they are 5, 0 and -2, 0. Now, the one that is -2, 0, because that factor up in my equation has an exponent that is not 1, it has a multiplicity, and it will have the multiplicity of that exponent. So this will be a multiplicity of 2. Not because the intercept is at -2, 0, and the multiplicity is 2 because of our exponent is 2. And then the number of turning points, we have 1. Now the number of turning points, we have 1 turning point here, which is also one of our x-intercepts, and we have another turning point there, so we have 2 turning points. Then example number 4. Okay, this is a funky looking graph, but we have our 2 factors here. The x minus 3 has a 3 above it as our exponent, and there's that invisible 1 here on x plus 1. So your degree is going to be 4. Your leading coefficient again is that invisible 1 in front. Number of distinct real zeros. Well, hopefully by now you've kind of gotten to the use of the fact that you could look at the graph, but you can also look at the equation. See, we only have 2 factors here. Look at a graph, we have 2 different zeros. Up here, we had 2 different factors, we had 2 different zeros. Here we had 4 different factors, and we had 4 different zeros. So the number of different factors that you have will tell you the number of zeros you have. So then our zeros are going to be -1, 0 and 3, 0, and that 3, 0 will have a multiplicity of 3 because our exponent for that factor was 3. You don't need to write multiplicity of 1. But this one has a multiplicity of 3. And then the number of turning points, well, let's see, we have 1 turning point here, okay, and then you look at that point there and you're thinking, well, is that a turning point? Not necessarily, because remember our turning points that we talked about, turning points are where you have a minimum or maximum. This point right here is not a minimum or maximum point, because your function, your graph is increasing, it's going up before, and then it's gets really close to not going up, but then it continues to go up. So there's only 1 turning point. Then this last example, our degree is going to be our exponents added up, so 7. Our leading coefficient is -4. And then distinct real zeros. So how many different zeros do we have? 1, just 2. And you look at the graph, 1, 0, and there's another 0. So they are -2, 0, and 5, 0. They both have a multiplicity though, and we look at that, the -2, 0 will have a multiplicity of 3. Multiplicity of 3. And the 5, 0 will have a multiplicity of 4. And then the number of turning points, there are only 2 turning points here, right here and right there. So we're going to use these 5 examples here to come up with a conclusion about the number of turning points in relation to the number of distinct zeros, or the equation. And then we're also going to look at the behavior of those x-intercepts. So it says, how are the number of distinct zeros and number of turning points, your minima or maxima, related to the equation? So if we look at the number of zeros in our equation, okay, the example 5 had 2 zeros and degree 7. Example 4 had 2 distinct zeros and degree 4. Example number 3 had 2 distinct zeros and a degree 3. So far the number of distinct zeros has been lower. Oh, here they're the same. Distinct zeros and degree is 4. Example number 1, it was 3 and 3, the degree and number of zeros. So what it looks like is that the number of zeros is always equal to or less than the number of, or the degree there. So number of zeros is equal to, let's write it mathematically, less than or equal to, less than or equal to the degree. So we could never have a 5th degree function with 6 zeros. We could have a 5th degree function with 5 zeros or 3 zeros or 4 distinct zeros, but the number of zeros can never be more than the degree. Now let's look at the turning points. Okay, the turning point here, the turning point is the same number as the number of zeros, but also less than the degree. Here the turning point is smaller than the number of zeros and smaller than the degree. Here the turning points is equal to the number of zeros, and the number of turning points is smaller than the degree. Here turning points is smaller than the number of zeros and the degree, and same thing here. So the number of turning points is less than the degree. So it can't be equal to, if I have a 5th degree function, there can't be 5 turning points. There could be 4 turning points, but there could also be 2 turning points, and there also could be 1 turning point, and so on. Then if we look at the x-intercepts, what are the 2 ways that a graph can behave at the x-intercept? Can we think of a relationship? So if I look at, here's a good one. This is a good one to look at. If we have our x-intercept here on the left, you see the function goes up, it touches that intercept, and then comes back. I call that a bounce. So the function or graph goes up, touches that intercept, and bounces back. Then here, the function touches that intercept and keeps going. So we cross the x-axis. Back here, we bounced off the x-axis. If we look at example number 5, if we follow the graph at this 0 right here, we cross the x-axis, we go through it. The next time we come to the x-axis, we touch it and we bounce back. We bounce off the x-axis. So if we look at our multiplicity of those zeros, when we crossed, our multiplicity was 3. When we bounced, our multiplicity was 4. Okay, up here, when we bounced, our multiplicity was 2. And when we crossed here, our multiplicity was 1. Because, if we don't have a multiplicity, it's always 1. So if we have an odd multiplicity, we cross the x-axis. If we have an even multiplicity, we bounce off the x-axis. So it's important to know the difference between these two, because if I ask you to graph it by hand, you need to know if you're going to cross or bounce off the x-axis at that 0. All right, so let's look at some examples down here. Example 6, what is a possible degree and leading coefficient for the polynomial? Now, we won't be able to determine what the exact degree or exact leading coefficient are, but a possible one. So if we look at this, we have 1, 2, 3 distinct zeros. So we know we have to have a degree of 3 or more. And because the ends go in opposite directions, we know the degree has to be odd. So the degree could be any odd number bigger than, or any odd number greater than or equal to 3. So it could be 3 or 7 or 11, anything like that. The leading coefficient, so abbreviated LC, because the right side is going up, it must be positive. So any positive number, so it could be like 24 or 9. Just any positive number. Remember, anytime the right side goes up, the leading coefficient has to be positive. Example 7, write a possible equation for the graph below. So again, you're writing a possible equation. There's more than one right answer. So when I do these, I always look at the leading coefficient, and I look at the right side. That tells me if the leading coefficient is positive or negative. Because the right side goes up, it is positive. So any positive number could be our leading coefficient. Then I look at each of my zeros. Okay, this is 4, 0, so that means I need x minus 4 as one of my factors. This is 0, 0, so that means x minus 0 as one of my factors, so we just write x instead. And then that is negative 5, 0, so we need x plus 5 as one of my factors. Now you may be checking this and saying, hey, this only has a degree of 3, and the ends are going in the same direction, they're both going up. And that's correct. Like we have to do something else here. This 4, 0, that x-intercept, our graph bounces off the x-axis there. So what that means is that the multiplicity must be even. So multiplicity must be even. Oops. So the exponent here, the x minus 4, has to be some even number. It could be any even number you want. Right. So that's just one possible equation. You could also have any of these other zeros, you could have an odd multiplicity there, because if your multiplicity is odd, you cross the x-axis. So there's nothing else in this problem to say whether or not the other two zeros have a multiplicity or not other than 1. So there's infinitely many answers you could have for this equation, this function here. So I hope that this made sense. I know that this can be a confusing topic, especially when you're talking about bouncing and crossing the x-axis. So if you need to go back and look at some of the previous things that we talked about, this thing is huge, this conclusion. Go back and look and see, okay, why did we say some of the things that we said? Because this is something that is going to come back for a while. So thank you for watching the video. Make sure you pound that like button and subscribe.